Hello and welcome to Connected Data London online meetup. Connected Data London is the leading event for those who use the relationships, meaning, and context in data to achieve great things. My name is George Anviotis, and among other things, I am Connected Data London's co-organizer, and I will be your host for this meetup. Today we have two talks. The first one is a panel discussion on facilitating COVID-19 research using graph analytics and knowledge graphs, and the second one is about connecting dots with real knowledge. We have been connecting data, people, and ideas since 2016. Our topics revolve around AI and machine learning, knowledge graphs, graph databases, and semantic technology. We are proud to have hosted a number of thought leaders and innovators from the likes of Bayer, the BBC, JP Morgan Chase, NASA, Uber, Zalando, Facebook, Google, and Microsoft, to name just a few. Normally, we have our face-to-face meetups in London and Berlin every couple of months. This is April 2020, however, and the world is in lockdown. So unfortunately, we're not able to do this. Since, however, we like to see problems as opportunities, we have taken this opportunity to open up our meetups for everyone, whether they are in the same location or not. And this applies both to attendees and speakers. And today we have the pleasure and the privilege of hosting some great speakers. So without further ado, let me introduce you to our first speakers. We have with us Dr. Søren Auer, who's the director of the Leibniz Information Center, head of the research group for data science and digital libraries, and also the lead of the Open Research Knowledge Graph project. And we also have Dr. Alexander Yaras, who is the head of data management and knowledge management at the German Center for Diabetes Research, and also a founding member of the COVID GRAPH project. This is fortunate timing, in fact, as it was just a few hours ago that we learned some very good news. So Søren has been included in the top 5 list of the most influential scholars in the field of knowledge engineering. Congratulations, Søren. And let us start the discussion with you. Let us talk about scientific research. At this time, it's a topic that attracts more attention than usual from a wider audience. The reason is that the scientific community across disciplines is focusing its efforts on fighting the coronavirus pandemic. While science is one of the pillars of modern society, it isn't without its own issues. What would you say are some key issues that apply to scientific research in general? And certainly those would apply to research in the life sciences as well.
We use still the same methods and artifacts like 500 years ago, basically static scientific articles. And if you look in other domains, the world of information sharing, knowledge exchange has completely changed. Imagine, for example, you would have to use a street map as a PDF document, scanned, and as a PDF document in order to navigate from A to B, or you would have to use a scanned mail order catalog to order products online by email. That's how we work in science. We use scanned or PDF documents, which is basically a very shallow digital artifact of what we had before the internet and the digital wave. And I think we need to, as other domains, as we have e-commerce websites, navigation systems, digital map applications, encyclopedias on the web, we, I think, need also to develop new means how to organize knowledge, scientific scholarly knowledge on the web and on the internet. Yeah, that's, from my point of view, one of the biggest challenges, because we also have huge investments into research, and my impression is it doesn't work very efficiently right now.
I see. This is a very valid point, and I would like to ask Alexander if he has anything to add to that, more specifically applying to life sciences, which is his own domain.
Yeah, I couldn't agree more with Søren. So he's extremely right. So in research in general, and especially here in the healthcare sector, data is not only scattered, it's very heterogeneous. And in terms of the FAIR principles, like findable, accessible, interoperable, and reusable, we are very unfair, I would say. And that has many reasons, historical reasons, and we definitely have to change that because in other industries or in other sectors, we have much more advances because of digitization.
Mm-hmm. And to make it a little bit even more specific, since this is the topic of the day, obviously, and since scientists from different domains are trying to cooperate and coordinate their efforts into research into the coronavirus. And I know, Alexander, that you have also been active in this field. Would you like to tell us a little bit about some specific issues that pertain to this research?
Yes, exactly. Thank you for mentioning that. We have an initiative called the COVID GRAPH, and we accepted a challenge by Kaggle, where they gathered roughly 45,000 preprint publications, so scientific publications from coronavirus infection and coronavirus research. Well, the problem is that researchers first have no time to read all of them, second to understand everything, and third to connect that to the biomedical, entities in biomedicine, being genes or phenotypes or diseases or symptoms or even drugs. So it's a problem that you have to cope with the literature, you have to cope with the databases, and this is what makes the researchers slow down, because it's too much information, and you have to provide a data source or like an acceleration for analyzing this data.
Mm-hmm. I see.
And this is where we try to support and try to provide the researchers a platform that has already some analyzed data and connected data from different databases in the medical field.
Okay, so it sounds like a typical, I would say, case for where knowledge management can help. And since even though we are all about knowledge management and connected data, since we may also have some fresh members of the audience with us today, what better way to give an introduction to that than ask one of the top minds in this area, Sharon. I wonder if you'd like to say a few words on, a little bit of gentle introduction, let's say, to knowledge management and how we can get from data to what is generally called AI today, through the different stages of analytics. And by doing that, it's also a very good opportunity to highlight your work in this area, which has been going on for many years.
Yeah. I think the main problem is a bit that we have this media breaks between knowledge, information in this area. We have static publications which are hardly machine processable. We have different data sets and different formats. We have a lot of heterogeneity. So we need to connect and integrate all this. And the typical answer of computer scientists, let's develop some information retrieval, some knowledge extraction, some natural language processing algorithms. And that's what we do for 30 years. And we are, in a way, successful, but we don't reach the level of precision and recall, which I think is required for real-world practical applications. Yeah, and what we need to put in the loop is the humans as well. If you look, for example, very famous platforms like Wikipedia, for example, Wikidata, a structured knowledge base, or another prime example of mine is usually OpenStreetMaps. And what you can see there is that it's not purely automated approaches, but it's a lot of crowdsourcing, and then also automated supported approaches supporting the curation of this data. And I think that's what we have to put together, that automated techniques, machine learning, AI, but at the same time also the human intelligence, putting humans in the loop for curating this information, for linking, connecting, and integrating that. And that's, from my perspective, the only way how we can solve this information problem by integrating, connecting information from different sources. And of course, we need to use semantic web standards, which were developed over the last 2 decades, like RDF schema, OWL, to represent information, to connect, to have a unified maybe paradigm for exchanging, linking, integrating information in this space. And also what RDF and RDF schema and OWL provide is we can integrate different levels of structure, unstructured information which is extracted or linked from texts with very highly structured ontologies which we have in the life sciences already, fortunately. And that's a bit, from my perspective, the challenge space we are facing here. And I would criticize my own field, computer scientists, that we focus too much on this purely fully automated approaches, and we don't see this holistic, that we have to involve crowdsourcing or expert sourcing and put human and machine intelligence in a loop. And that's, from my perspective, one of the biggest challenges to make research and scholarly communication more effective.
That's true, and I think as a kind of answer, let's say, to your criticism, which is actually very fair, I think more and more researchers and technologists are realizing this point these days and trying to combine and make this kind of hybrid, let's say, systems. You also touched upon structured versus unstructured data, and you specifically mentioned Wikipedia. And since I know that there is a structured version of Wikipedia, which is called DBpedia, and you have been one of the forerunners.
Now also Wikidata, of course, is integrating that even better with Wikipedia than DBpedia did.
Mm-hmm. Yep. I wonder if you'd like to say just a few words about that as an example of mixing the two approaches, basically. So going from unstructured or semi-structured data, which is Wikipedia, to structured data.
Yeah. So with DBpedia, we basically extracted semi-structured information from Wikipedia, and that was already an advantage that other than traditional encyclopedias, which were basically printed documents or PDF documents, we had already some kind of semi-structured information pieces in Wikipedia, which are these fact boxes, which is the category system, and a few others. And this could be extracted from the source code of the Wikipedia pages and then represented as a knowledge graph. So we extracted this information, mapped it to statements and facts, and made this available as a large knowledge graph, which then can be queried. And of course, the precision and the accuracy of this knowledge graph was not perfect, because this extraction approaches from the Wikipedia pages had a lot of smaller issues. So there were some things which were not correctly extracted, but it already provided and showed a bit the vision, and I think that gave rise then to the Wikidata, for example, which is an initiative to integrate that much more tightly into Wikipedia and organize the information in a more cleaner and more precise fashion. And so that allows them to run some structured queries, to ask questions, to use question answering, which we are already used to. If you think of assistant services like Amazon Alexa or Google Now or Apple Siri, and for question answering, we need such structured knowledge, and that's what we can use with knowledge graphs. And I think we need the same for science and for scientific information, that we can ask, what's the state of the art in a certain field? How does this approach compare to that one? And then get real machine assistance to answer our information.
Yeah, it sounds perfectly plausible, and I know that you have been working on that actually, and I know, because we talked earlier, that you would like to show a little bit of demo on your latest work. While you do that, while you get ready to share your screen and share the demo with us, I may as well return to Alexander to ask if there is any of these principles applied to the COVID graph effort. I mean, I'm sure that there is a certain structure behind scientific publications, and I wonder if you use that in your graph, and in what way.
Well, the structure of the literature data is more like, bits and pieces of identifiers, of text blocks, of just lines of text, words. And so in the beginning, in the first 2 weeks, we took a lot of effort to structure that data, to bring that into a data model that you can query afterwards, and then bring it to other, let's say, data silos. We connected not only scientific publications, but also patents that are in the field of coronavirus in general. And then we connected this together with the biomedical entities, being genes and proteins and diseases and tissues. So there was a lot of effort, and I agree with Søren that this is an approach that is not necessarily or specifically done with artificial intelligence or whatever machine learning efforts. You have to have expertise in the domain. You have to have experts that are looking over your data sets and making sense out of it, structured in a way that a human can read it, in order to have a very powerful data set and having a structure that you can query.
Mm-hmm. Yeah, I guess just by listening how you describe some of the key entities, I guess, that pertain in your domain, such as a gene or a pattern or a molecule, I guess that these are somehow modeled in your graph, and you use them as a kind of class which you populate with instances in a way.
Yes. So we have it as classes or entities in our knowledge graph, and we use the expert knowledge from some of our researchers to connect new types of data or new data sources, and also to have a user interface that especially non-computer scientists can use it, because in the end, most of the scientists are non-computer scientists or not familiar with querying or with managing huge amounts of data. So we try to put that behind a graphical user interface, so that in our case, medical researchers or doctors can use it.
Mm-hmm. Okay, I see. So let's switch back to Søren, because I think now we are ready for him to show us the little demo he had prepared.
Yes, but it still says that you are sharing your screen. It's just paused. And I somehow don't find a button where I can do that, George.
I'm sorry, Søren, there was a little bit of problem with my connection and lost your last sentence. Would you repeat, please?
Yeah, it says that you are still sharing your screen. It's
I have stopped now, so I think you should be able to do that.
Great. Okay. So I hope you can see it now. And I hope you can see now the Open Research Knowledge Graph website, and what you see here is a comparison. So Alexander, please correct me if I say something wrong. I'm of course only hobby now virologist or epidemiologist, as almost all of us. Yeah. And,
exactly. Yeah. Everyone is these days like an armchair epidemiologist. Yeah.
Exactly. And one important question which is often discussed in the media is this basic reproductive number of the coronavirus. And there are a lot of papers. We actually found a survey. There were 10 papers or 12 in the survey from China. And then the first papers appeared from Italy, which analyzed this basic reproductive number. The problem now is, if you are interested in how do this assessments from different researchers compare, how did they what values did they get to, in what time frame did they perform their analysis. You have to read all these papers, and you might miss something. And if you find a survey, then maybe it is outdated because now it's a very active research area. So what we did is we imported this initial data from the survey into a comparison, basically into a description. And what you can see here is each column in this table corresponds to one publication, and then we added to the rows of the table basically different characterizations of the approaches or of their analysis. And for the basic reproductive number of COVID-19, which is basically the number indicating how many people are infected by one infected person. So current estimates go that it's around 2.5 to 3.5 if there are no measures applied. And here we see the studies which actually came to this R0 estimate. And you can see that in the fourth row, the R0 estimate coming from a certain study. You then can also see the 95% confidence interval. For this first study, the R0 value is 1.97, and the confidence interval is between 1.45 and 2.48. And then we can describe how the approach was for assessing the this R0 number, what methods they used, and we can then compare different approaches. And you see here that meanwhile it's a relatively large list of publications. I think we have around 30 now. I can also switch to full width mode, where you can basically compare the different or have on a bird's eye view the different publications assessing this R0 value. And the table, of course, gives you already a bit more compact information. You can now relatively quickly look who has studied this value, in what region, in what time frame. But even better would be, of course, if you have some visualizations. And since the information here is in a knowledge graph, in a kind of structured database, we can then also create visualizations. And if you click, for example, on the link below, you will see different types of visualizations. For example, how the estimates were published over time as a chart, a first chart. In a second, you have a bar chart with the R0 estimates. And in the third chart here, we have also indicated the confidence interval. And there you can pretty much see that it's between 2.5, 3.5. Of course, this is a question which was already in a way answered, and there are thousands of people looking at these publications. But the same method can be applied in the Open Research Knowledge Graph to all kinds of research. So we have a very flexible model. What you see here, for example, is how one particular publication is represented in the graph. It contains two different contributions, and each contribution contains basically facts and certain information about the publication. And that allows you then also to look at it from a graph point of view, and you can expand different parts of the graph and navigate through this knowledge graph basically. And it's linked with other publications, with research problems and research fields. But of course, it currently requires also manual interaction. It's not possible to fully automatically create that, but it needs to be curated by humans. And of course, we also apply some support techniques to assist humans leveraging natural language processing, artificial intelligence.
Mm-hmm. Actually, you just touched upon the question that I was preparing to ask you throughout about halfway your presentation. It's very impressive. It's great work. I was just wondering how much of that is manually curated and coded versus how much of that is extracted.
Currently most of it is manually curated, but also what is important is you don't need all the information from a paper. But for example, for this basic reproductive number, you're interested in 2-3 values, which is basically the reproductive number value, the 95% confidence interval, the region where they did their analysis, and maybe the time frame when they did that. So these are 3-4 values which are relevant, and that's first relatively easy to add to the knowledge graph. And the second is, of course, we also now develop techniques to automatically extract such information from the papers. But this is relatively cumbersome, and we reach maybe 70, 80, in the best case, above 80% precision and recall, but it still means that 10, 20, 30% of the values are not correct. And that, of course, also annoys the users a bit, and that's why we are still figuring out what's the right balance between automatic extraction and manual curation.
Yeah, of course. But even if you have an accuracy about 70 or 80%, that's something, because then you can apply manual curation and bring it up to 100%. So,
yep, exactly.
Mm-hmm. Okay. And Alexander, to switch to you, I know that you also wanted to share something to show us a little bit the COVID graph and how does it look.
Yes. So where can I share my screen? Button.
In the main area of the screen.
Got it.
Yeah.
So so you should see my screen now.
Yes. We.
And so the one thing that we have is the knowledge graph itself, which has different visualization tools because we are collaborating with different companies there that contribute to this project. And I will show you 1 or 2 examples now, what we can do. First one is, maybe I give you here a screenshot here. We did an analysis of genes that are mentioned in the publications. So we had a natural language processing procedure that recognizes genes in text automatically and connects them here. And we have the genes now here in the screenshot. You see it in green. Mm-hmm. You have a gene that is mentioned in a specific paper, or here on the bottom, there's a paper that mentions different genes. And these publications are, of course, connected to their authors. And what we did is a centrality algorithm that we run over all the genes in the papers to find out the gene or the genes that are most relevant in the coronavirus field. Let's say it like this. And this was here, this guy. The gene is called ACE2. And you can see here that many papers are mentioning this gene. And now we had the first question, why is that? And this is pretty obvious if you're a biochemist or a medical doctor, because ACE2 is the receptor that the virus uses to intrude the cell. Mm-hmm. So it makes much sense that many publications are mentioning this gene because they want to study the strategy of the virus and how to protect that maybe. And this was like an analysis that was done using algorithms on top of our knowledge graph, and then point the researchers here to a more focused set of publications. So this is one example where we use algorithms. Second example I can show you here live on the database, where we can put a query here in semi-natural language, as we say. So the user can write a query like, give me the genes that are mentioned in a paper with diabetes. And with diabetes is just one example because I'm working for the German Center for Diabetes Research. And when I click on that query, people that are non-computer scientists, as I say, they can enter queries and get examples back. And I hope that this is fast now here. So it's a little bit slow. But you see already the papers that are actually written in terms of coronavirus, but there are genes that are diabetes relevant. So there's an overlap between two severe diseases, and there's a fact that diabetic patients have a higher risk to get infected and a higher risk to die. So there is evidence, or there is there's a connection between the two diseases. And this is what the researchers here can see. And we can manually interact with this graph here. And this is what Søren also mentioned. A knowledge graph, in my definition, is not a static result. It is, let's say, the result of this analysis here, of this query, is just the beginning of the next query, or is just the beginning of the next investigation of something. And as I can zoom here, I can drag and drop the papers. The papers are here in blue, and the genes are here in pink. And you can now cluster these genes, cluster them according to their gene function, or cluster them according to another disease. And this is what makes the interaction with the knowledge graph pretty easy to have a good visualization. So this is one of the examples that I can show here so far. There are many other let's say use cases that we already written down in our GitHub repository. So there are use cases from patent lawyers. There are use cases from medical doctors, also from basic researchers, and we are trying to answer these questions and try to support them now with the COVID GRAPH project.
Yeah, I can see, because I was already kind of familiar with your work, because we did an article on that. Mm-hmm. So I checked it out a couple of weeks back, and I can see that you have already made some progress compared to what you had then.
Yeah, thank you very much.
Mm-hmm. So this example that you gave in a kind of not exactly natural language querying, but close, is it already makes things much easier for users who are not necessarily familiar with the graph query language that you use.
Exactly, and in many cases, these questions are very simple. When you speak to other people, they are pretty simple, but not so easy for a machine. But the point is that many of the researchers ask the same questions, and so we try to gather these. And collect these use cases or these queries and provide them in a natural language way that people can enter a normal sentence.
Mm-hmm. And then, as you also pointed out, this is actually how this is a very good way to actually do data exploration using knowledge graphs. So you start with a query, something specific that maybe you're interested in that point, and then you should be able to explore. So does this visualization also serve these goals, or are you able to drill down, let's say, in a specific node if you wish?
Yes, so I can click here on, let's say we take this paper here. It's a little bit slow today because we are heavily working on the database. And then you can select this paper and, does it work? Oh, it doesn't work. Let me show it on the screenshot here.
Okay.
So here on the screenshot, when you click on one of the publications, you will easily get the authors, the abstracts, the mentioned genes, the mentioned diseases. Sometimes there are 2 diseases, or sometimes there are some phenotypes or other keywords that are mentioned there. So you can easily interact with them. What you also can do is we have, let's say, typical graph algorithms already implemented, like shortest path. You can select 2 nodes and can ask the question, what is the shortest path between the two nodes? And then having the result going to a researcher and ask the question, does that make sense at all? And this is also what Søren meant. In many cases, just pure data analysis or just pure machine learning doesn't make any sense. And so you have to have specific information coming from human interactions. Yeah, I think it's very useful to see those 2 approaches and implementations side by side, and to hear you both describe a little bit how they work and what the rationale is behind them, because I think it also highlights, strong points in 2 different approaches, basically.
Again, this is kind of common knowledge for people who are into graph modeling and knowledge graphs, but let's repeat for the new members of the audience among us that broadly speaking, there are two approaches in modeling graphs. One is called property graphs and the other is called RDF or semantic modeling. And well, it's, going into the details of how each approach does what is very, very long and nuanced discussion. But the point that is actually probably more important here is basically how would we work if we wanted to combine, let's say, those two efforts? So we have here one knowledge graph, the Open Research Knowledge Graph, which is modeled using RDF. And we also have a COVID graph, which is modeled using property graphs. So I would like to first address the question to Søren. How would you go about combining these two knowledge bases?
We actually did already, like the Open Research Knowledge Graph is a property graph and RDF. We use Neo4j as a basis for the implementation. So underneath it's a property graph, but of course we integrated or layered the RDF data model on top. Why did we do that? Because we wanted to have the scalability of property graphs, so they scale horizontally, which is a very nice property. And at the same time, we wanted to have the expressivity of RDF, and that's why we integrated both in a way. Also, property graphs are a bit more flexible. You can add easier meta information to the properties, to the statements in Sparkle triple stores and Sparkle databases. That's usually a bit more challenging to add reifications or information about meta information about the statements and the triples. On the other hand, of course, it's still also a challenge. So we don't have direct Sparkle querying support. We currently load the data from the Neo4j database into another Sparkle endpoint in order to provide the possibility to allow to query it using Sparkle. And so there are still a number of challenges to integrate both, but I think it's definitely feasible. And there are also even commercial services like BlazeGraph, which got acquired by Amazon and is now Amazon Neptune, where they have something integrated property graph and RDF functionality in one technology, basically.
Mm-hmm. So you're saying, if I got you right, that you are keeping, I guess, the information in two different instances, right? One as a property graph and the other one as an RDF graph, and you can you need to synchronize them, but you can query both. I think, Søren, I think you're...
Sorry, I was muted, yeah. The ground truth is in the property graph. So we use Neo4j as the central point of truth there. All the data is in the Neo4j graph. But of course, we organized it there in a way that we have identifiers, URIs for the entities and for the nodes and edges, so that we can easily export it as RDF. And there are some experimental additions to Neo4j which allow some kind of Sparkle querying, but they were not so mature yet. So that was the reason why we have another Sparkle endpoint triple store on the side. But of course, in the future, I hope it will be directly integrated also into property graphs, that you can query them using Sparkle and use RDF and RDF schema and ontologies out of the box. I think the main difference is that property graphs don't have this unique identifiers, these URIs which you can use, and then of course a number of interfaces and APIs like Sparkle or link data, while triple stores have that built in. But it would be great to have both together, of course.
Mm-hmm. Yeah. How about you, Alexander? Do you use any elements of RDF modeling, or would you like to actually, such as URIs that Søren just mentioned?
Well, we don't have any RDFs already in the graph. I would say our also Neo4j based is a mixture of both. So we have a property graph, typically from the different entities, and since we are heavily working on the graph itself and try to learn things and infer things and predict connections, I think it's turning more and more to a knowledge graph itself. Yes, from this perspective, I would say we have both. But of course, it would be beneficial to have the one or the other API where we can jump from one to the other database.
Mm-hmm. Okay, thank you. So I think we've covered a lot of ground, and we're kind of fast approaching to wrapping up. And this is a point where we actually take questions from the audience, and I see that we have a few. So first question from Peter is whether the system is live somewhere that we can explore, and I can answer this one for you. So yes, both systems are live. COVID GRAPH, you can actually just type them in any search engine, and I'm pretty sure you will find them if you search for COVID GRAPH. I think the extension is covidgraph.info.
.org.
.org. Okay. And the Open Research Knowledge Graph, it also has its own domain, which is ORG, if I'm not mistaken, Sharon, right? So yes, quick answer, yes, both systems are live and you can test them and have
yes, absolutely.
Mm-hmm.
I shared the link also here in the chat.
Yes, please do, so that the audience can quickly check that. So the next question is from Tariq, and the question is, what are your suggestions for graphs which are overly dense, thus making visualization and interpretation difficult? So sometimes the question goes on to add, filtering properties to reduce the data in a view isn't an easy option. And I know this is something that both of you will have an opinion on, because the data sets that you have to deal with are really quite big and quite dense. Let's start with you, Sharon.
Sorry, I was a bit busy typing the link again to the chat. So it was about
visualization, basically, how to work with very dense graphs that are hard to
right. Yeah, that's a good question, and that's very important. Visualization. If you have a large graph, it gets cluttered and it's very difficult to keep an overview of the graph. So I actually have a very good PhD student, Vitalis Wiens, who is working particularly on that topic. And he developed several approaches where you, for example, one is called semantic zooming, that you can zoom in and out in the graph. And it disables or clusters and deactivates certain nodes and edges depending on the zoom level. The same way as when you zoom into a map or out of a map, you see smaller roads or you don't see smaller roads and buildings and so on. And the same way, I think we need to support this when we visualize graphs. Another approach Vitalis developed is for styling the graph in a way that you can add different types of colors and icons, that you maybe can also use styles which people are familiar with, like UML visualizations, for example, or there are other visualization types in different communities. And when we have the styling option, it also makes people being a bit more familiar. And there are a number of these techniques, but of course it's still also a research issue to make it really scalable, also to visualize. For example, we want to visualize comparisons between different graph representations of scientific contributions, and we are still researching and writing papers about that, and at the same time then integrating new functionality also into the Open Research Knowledge Graph.
Mm-hmm. Mm-hmm. Good. And how about you, Alexander? I mean, I saw that you also had some pretty dense visualizations there.
Yeah, exactly. And these are exactly the problem. So we call them super nodes. And so the one thing that we use is the visualization by Linkurious, which is a company who are doing a visualization on graphs and with Neo4j. And with this, you can define different aggregate functions, saying that you can aggregate over, like all the relationships from one type that are represented only by one relationship. And then according to the number of relationships, you have a thickness parameter that you can give a specific relationship. Another, to me, a new tool is called SemSpect. I will put that link also into the chat, and they have a very smart way of representing the graph. I can show you that here on my screen. Let me share the screen again.
Yeah.
And this is a very smart way of representing that. I don't know, Søren, if you heard about this. These are it's a German company from Ulm.
Yeah, absolutely. Yeah, they do good work.
Let's say here they have a very nice video here on Vimeo, and there's a super set of nodes here that is connected by the edge has subject. So an article has a subject, right? And here are 5,000 articles here, and there are a lot of subjects, and they are clustering these nodes, and then you have a specific D3 visualization on top of that are summarized here in one or the other edge. And you can go specific edges here, as you can see here. And let me pause that. So between the red supernode and the light blue here, there are actually 80 edges that are summarized in just one very nice edge here. So this is what we try to use to circumvent this problem of these supernodes.
Mm-hmm. Okay. I think we only have time for one more question, and we have a lot, which is a good thing. Unfortunately, we can only choose to address one. So I will have to choose something which again is a kind of common recurring theme. So how do you deal with relationship extraction? Because this is something, again, that both of you have to do to populate your graph. And starting with you, Søren.
Yeah, so I think this is the most challenging problem and question. And I think actually open domain relation extraction, from my perspective, doesn't work. It works when you exactly know what you are looking for. For example, for this R0 values, which I presented, if you know you look for a number and there should be something like basic reproductive number before or afterwards, then you can probably identify this number and identify the relationship that this is the basic reproductive number. But I think in many cases, it's relatively challenging to reach sufficient precision and recall for relationship extraction. And that's, from my perspective, the most challenging part, because what we can do relatively well is identify entities, named entities in documents, but connecting how the relationship between them, and that's what makes the graph really interesting. You want to compare approach A with approach B, and for that you need not just to know what named entities are occurring, but you need to know how the relationship between them is. And that prevents us currently, from my point of view, of really making sense of the scientific literature on a large scale. And I also think we will not be able to do this fully automatically, especially since we scientists, we write papers also not always in a very clear manner. We are sometimes ambiguous. We sometimes want to even hide some information from the papers in order to increase our chances of getting accepted. And it's already for us very difficult to figure out what's going on in a paper. And for a machine, it's, I would say, almost impossible. Or we need really a lot of good training data for doing that. And unless we have this, I think we need to really involve humans in the loop and tap this human intelligence there. So it was a long answer. Did I shut everybody down? George is looks like he's a bit offline. Alexander, do you have want to continue on that?
Yeah, I can only agree with you for the whole interview here. I really think the same. We definitely need human interaction with this. We are trying to infer different things in the knowledge graph and automatically create new edges after an analysis. But this is only true for a very, very small type of data or type of experiment. On a large scale, this is not possible, and this is exactly because the variety of literature and the variety of ways how you can describe the same thing. I guess we are far away from covering all that. Yeah.
So George is typing here in the chat that we need to wrap up and close. It was a great experience to participate in the webinar. I hope I can participate at some point live also in Berlin or in London. And if you want to get involved, at least for the Open Research Knowledge Graph, but I guess for Alexander it's the same. Our project is fully open source, open knowledge, and we are interested, everybody can contribute to that. And we are in particular interested in adding some COVID-related research information to the graph. So if you have some ideas, please send us an email and get in touch, and we will be happy to collaborate.
Yeah, the same is here. Of course, we are a limited number of developers, and so help is always appreciated. And also, if you have a scientific question or if you have, let's say, a data set that makes sense to be integrated, please, get in touch with us, and we can also help you with analyzing different queries.
Hello, this is Elias from CTL team.
Hi.
George's connection just went down, so I must step in and make, first of all, say thank you to both of the speakers. I would like to thank everybody that attended, and we have some very great feedback that it meant something for them, and that they learned something. So let's wrap it up. Thank you everyone for attending. On the chat there is the link for our second discussion that will start shortly. Thank you very much for presenting and for participating.
Thank you.
Thank you very much.
Bye-bye.
Bye-bye.